This is sections 8.6 and 8.7 of Honors Algebra 2, Roots of Polynomial Equations. So, remember, a root of an equation is a value that makes the equation equal to 0. So in this case, numbers that I would plug in for x that would make the equation equal to 0. So I've given you 4 different types of polynomial equations here, an example of each one, and we know how to solve all 4 of these examples. Take the linear equation, x plus 3 equals 0. That's easy to solve. I just subtract 3 from both sides, and x equals negative 3. So the value for x that would make the equation equal to 0 is negative 3. Thus, the root is negative 3. How many roots are there? There's only one. I got no other solutions, and there are no other numbers that I could plug in for x that would make this equal to 0. What's the degree of this equation? The degree is the highest power of the variable. So what's the degree here? 1. X is x to the first power. So it has a power of 1, and there are no other higher powers of x. Alright, take the quadratic equation, x squared minus 4x plus 13 equals 0. I know how to solve that. It's not factorable, but I can still solve it using the quadratic formula. So negative b would be 4 plus or minus the square root of b squared, which is 16, minus 4 times 1 times 13, and 4 times 13 is 52, so I'll have 16 minus 52. That'll be negative 36 all over 2 times 1, 2a. So these values of x equals 4 plus or minus 6i over 2, so x equals 2 plus or minus 3i. Okay, so my roots are 2 plus 3i and 2 minus 3i. How many roots are there? There are 2 of them. They are conjugates of each other, notice. And what's the degree of this? Well, the highest power of the variable is 2. Let's take the cubic equation, x cubed plus 4x squared plus 4x equals 0. I know how to solve that because this happens to be factorable. I can take an x out of every term and have x times x squared plus 4x plus 4. And then I can use the quadratic formula and x squared plus 4x plus 4. Or factor that as x plus 2 times x plus 2. So my roots are x equals 0, x equals negative 2, and x equals negative 2. So 0, negative 2, and negative 2. How many roots do I have? I have 3 of them. Negative 2 counts twice because x plus 2 is a factor 2 times in my polynomial. What's the degree? Well, it was an x cubed, so it's 3. The quartic polynomial, x to the 4th minus 10x squared plus 9 equals 0. Quartic is the name we give to a polynomial of degree 4. So this is a 4th degree polynomial. And I happen to know how to solve this one because it happens to be factorable using the methods we used last semester to factor things. Because there's no x cubed term, there's no x term. So I can do it as x squared and x squared. Those multiply to give me the x to the 4th that I need. And then I can do negative 9 and negative 1. Now both of those are a difference of squares, so they're both factorable. X minus 3, x plus 3, x minus 1, x plus 1. Oh, what are my roots? They are 3, negative 3, 1, and negative 1. How many of them do I have? I have 4 of them, and the degree was 4. Do you notice a pattern? You should, because you should notice that the number of roots always equal to the degree. Is that a coincidence? I think not. And indeed, it's not. And I can summarize that in a theorem. Every polynomial equation with complex coefficients, so they could be imaginary or real or a combination of them, and positive degree n has exactly n roots. That's exactly what we just discovered. Every polynomial equation, though, not just the ones that I gave you, if it has degree n, it has n roots. If it has degree 8, it has 8 roots. Some of those could occur more than once, like the 2 did in one of those examples. But if I count that up, it'll always be the degree of the polynomial. And we also noticed that when we had imaginary solutions, they occurred in pairs, and a conjugate was always an imaginary, a conjugate was always a solution. So if a polynomial equation with real coefficients has a complex number a plus bi as a root, which means a and b are real numbers, I is the square root of -1, and b is not equal to 0, because if b equals 0, this would just be a plain old real number. So if a plus bi is a root, then its conjugate, a minus bi, is also a root. So remember, that is the conjugate of a plus bi. The conjugate means I change the sign in front of the imaginary term. So that's powerful information. Because let's say I have this problem. Find a cubic equation with integral coefficients, so the coefficients are integers, that has 2 and 3 minus I as roots. Let's say cubic equation, so what do I know about that? I know it must have 3 roots. Cubic is x cubed. So I know it must have 3 roots. I'm only given 2 of them, 2 and 3 minus I. However, I know that since I have a complex root, its conjugate must also be a root. So 3 plus I must also be a root. They have to be that way. Okay? So how do I use the roots to find an equation? Well, I take x minus each of my roots. So I'll take x minus 2. If 2 is a root, then x minus 2 must be a factor. I'll take x minus 3 minus I, and I'll take x minus 3 plus I. And that must equal 0 if these are going to be roots. Okay? So x minus 2, let's just simplify in here. X minus 3 minus I is x minus 3 plus I, because I distribute that first minus sign, times x minus 3 minus I. That equals 0. Okay? Now we want to FOIL this out. It's generally easiest to start with the complex ones, because then the i's will nicely cancel. And then we'll multiply by the x minus 2 that's in the front. So x times x is x squared. X times -3 is -3x minus ix. Take the -3 now. I'll have -3x plus 9 plus 3i. Then take the I, and I'll have plus ix minus 3i minus I squared. I squared is -1, so minus I squared is minus -1, which is plus 1. Okay, I simplify that whole thing. I'll have x squared. I've got a -3x and another -3x will make -6x. That negative ix and the positive ix cancel. I've already taken care of the -3x's. I've got 3i and -3i, they cancel, and I've got 9 plus 1, which is 10. So you can check my math, but it's right. That whole thing simplifies to x squared minus 6x plus 10. So x squared minus 6x plus 10 is a quadratic polynomial that has what as roots? Well, 3 minus I and 3 plus I. That's how I formed it. So if I were to use the quadratic formula on that quadratic equation, I would get 3 minus I and 3 plus I as my solutions. Alright, now let's multiply in the x minus 2. So I'll multiply it by x. I'll have x cubed minus 6x squared plus 10x. And then I'll multiply everything by -2. -2x squared plus 12x minus 20 equals 0. I'll simplify by combining like terms and writing everything in decreasing powers of x, so starting with x cubed. The -6x squared minus 2x squared is -8x squared. 10x plus 12x is plus 22x minus 20. So now I have found a cubic equation with integral coefficients. Notice all of my coefficients are integers, that has as its solutions 2, 3 minus I, and 3 plus I. Are there others? Yes, there are. I could just multiply that whole equation by a real number, like 6, and I'll have another cubic equation that has the same roots. can multiply it by any real number that I want. So there are actually an infinite number of cubic equations that has those roots. I was asked to find one of them, so I did. Number 2. Solve x to the fourth minus 12x minus 5 equals 0, given that negative 1 plus 2i is a root. Okay? And as soon as I see that I have a complex root, I think I know its other root. A other root is its conjugate, negative 1 minus 2i. So I've got 2 of the roots. But this thing has a degree of 4, so there must be 4 roots. I know 2 of them. Okay, well, let's see what I can do with that information. If negative 1 plus 2i is a root, then x minus negative 1 plus 2i is also a root, is a factor. And the other factor would be x minus negative 1 minus 2i. I know those 2 roots, so I know those 2 factors. So let's multiply those out and see what that gives me. All right, x, distribute the negative sign, I'll have plus 1 minus 2i, x plus 1 plus 2i. FOIL it out. Multiply by x, I'll have x squared plus x plus 2ix. Multiply by 1, I'll have plus x plus 1 plus 2i. Multiply by negative 2i, I'll have minus 2ix minus 2i. And then negative 2i times 2i is negative 4i squared. I squared is negative 1, so that's positive 4. Combine like terms, x squared. I've got an x and an x, that's a plus 2x, so I'm taking care of those. I've got 2ix minus 2ix, those cancel. I've got 2i, negative 2i, those cancel, and I've got 1 plus 4, and that's 5. Okay, so I know that x squared plus 2x plus 5 is a factor, essentially, of my original polynomial, because I formed it by multiplying 2 factors of it. I can take my original equation, x to the fourth minus 12x minus 5, and I'll put in zeros for the x cubed and x squared terms, and I can divide that by the quadratic factor that I know, x squared plus 2x plus 5, and since that is a factor of it, I'll have a remainder of 0 and another quadratic factor, and I'll be able to solve that one to find the other 2 roots. So this is where polynomial long division comes into play. So I take x to the fourth divided by x squared, I get x squared. I multiply by x squared, I have x to the fourth plus 2x cubed plus 5x squared. I subtract. X to the fourths cancel as they should. I get negative 2x cubed minus 5x squared. I bring down the negative 12x. I take negative 2x cubed and divide it by x squared. I get negative 2x. I multiply by negative 2x. I get negative 2x cubed minus 4x squared minus 10x. I subtract. First terms cancel as they should. I get negative 5x squared minus negative 4x squared is plus 4x squared, so that's negative x squared. Negative 12x minus negative 10x is plus 10x. That's minus 2x. I take negative x squared divided by x squared. I get negative 1. I multiply by negative 1. I get negative x squared minus 2x minus 5. I bring down that minus 5. I subtract. And hey, everything cancels and I get a remainder of 0. Hey, I told you I would. So I did. And I know then that x squared minus 2x minus 1 is another quadratic factor of my original polynomial. So I took my x to the fourth, my quartic polynomial, and now I've broken it down into 2 quadratic factors, x squared plus 2x plus 5 and x squared minus 2x minus 1. I don't need to solve x squared plus 2x plus 5 because I already know those roots. I use them to find x squared plus 2x plus 5. Those are negative 1 plus 2i, negative 1 minus 2i. So I just take x squared minus 2x minus 1, the quadratic factor I just found, and I solve that one, I'll find the other 2 roots. Make sense? If not, think about it. So x squared minus 2x minus 1 equals 0. If I want to find the roots, it must be equal to 0. Is that factorable? So negative 1 and positive 1 will not combine to make negative 2. So it's not factorable, but I can use the quadratic formula. That's always fun. So I get x equals negative b, which is 2, plus or minus the square root of b squared is 4, minus 4 times 1 times negative 1, so that's going to be plus 4. 4 plus 4 is 8, all over 2 times 1 is just 2. So x equals 2, plus or minus 2 root 2 over 2. That means x equals 1 plus or minus root 2. Okay, so what are my roots? My roots are negative 1 plus 2i, negative 1 minus 2i, 1 plus radical 2, 1 minus radical 2. And notice we could not have solved that without the theorems from this section. But now we know how to solve it, which is pretty awesome. Another useful theorem is called Descartes' rule of signs. Let p of x be a simplified polynomial with real coefficients and terms arranged in decreasing degree of x. So arranged the way we normally arrange them. And the coefficients must be real numbers, so not imaginary. The number of positive real roots of p of x equals 0 equals the number of variations of sign of p of x, or is fewer than that number by an even integer. So I count up how many times the signs change in the terms, so how many times it goes from positive to negative or negative to positive. That is the number of variations of signs. So the number of positive real roots will be that number, or be smaller than that by an even integer. So subtract 2, and I'll have another option. The number of negative real roots of p of x equals 0 equals the number of variations of sign of p of negative x, or is fewer than that by an even integer. So that probably makes no sense to you right now, and that's okay. Let's look at an example. List the possibilities for the nature of the roots of the equation p of x equals 0, where p of x equals x to the 5th plus x to the 4th minus 3x squared plus 4x plus 6. Okay. So according to Descartes' rule of signs, since I've got real coefficients, and this is written in decreasing powers of x, I have to count the number of times the sign changes. So it starts out positive, still positive when I get to the second term. Then it turns to negative, so that's one change. There's one change, from positive to negative. And then it changes from a negative term to a positive term, so that's a second change. And then it stays positive after that. So that's 2 variations of sign. Okay? So that means that the number of positive real roots is either 2, or it said it can be lower than that by an even integer. So if I go an even integer lower than 2, my option is 0. I can go an even integer lower than that, but that would be negative 2, and that doesn't make sense. I can't have a negative number of roots. So I either have 2 positive real roots, or I have 0 positive real roots. Okay? Then Descartes, who, by the way, is René Descartes, the same man that the Cartesian coordinate system, the Cartesian graph system that we graph the x and y points on. Same man who did that, same man who was a philosopher who said, I think, therefore I am. Same guy, awesome guy. So p of negative x is what I get when I plug in negative x for x in my equation. Okay? A negative to an odd power is always negative, a negative to an even power is always positive. So that's the trick here. Negative x to the 5th is just going to be negative x to the 5th. Negative x to the 4th is just going to be x to the 4th. Minus 3 times negative x squared is going to be x squared. And then negative x times 4 is negative 4x plus 6. Okay, so that's p of negative x. Now I count the number of variations of sign. So it starts out negative, then goes positive. That's one variation. So then it's positive, then it becomes negative again. That's a second variation. But then it's negative, so it didn't change there. But then it changed from negative to positive. So that's a third variation. 3 variations of sign. That means the number of negative roots, negative real roots, I should say, is either 3, or decrease it by an even integer, so subtract 2, and I get 1 as my other option. So it's either 3 or 1. Okay. What does that all mean? So let's list out possible scenarios. I've got number of positive real roots. I've got a number of negative real roots. And if it's not a real root, positive or negative, then it's an imaginary root. So I've got it. The rest of them are imaginary roots, a number of imaginary roots. Okay. The degree, that was 5, tells me each row of this table must add up to 5. Okay? So one option for the number of positive real roots was 2. If I have 2 positive real roots, that leaves 3 other ones. Okay? They could all 3 be negative real roots. That was an option. That leaves no imaginary real roots. So that's one option. The other option is I have 2 real roots, and let's say I have 1 negative real root. Okay, that's 3 total. That leaves me with 2 imaginary roots, and that's fine. Imaginary roots, remember, occur in pairs, so there must be an even number of them, so this is okay. Alright, so I've exhausted the options of 2 real roots, but if I have 0 real roots, that was my other option. Well, that leaves 5 roots that are either negative or imaginary. I didn't have an option of 5 negative real roots, so I could have 3 negative real roots and 2 imaginary ones. That adds up to 5. Or I could have 0 positive real roots, 1 negative real root, and 4 imaginary roots. 2 pairs of conjugate imaginary roots, and that's fine. That row adds up to 5. So those are my 4 options. And if I knew more about this equation, I could maybe determine which of those options was the correct one. Let's suppose that you want to solve the equation 2x to the 4th plus 3x cubed minus 7x squared plus 3x minus 9 equals 0. That is a quartic polynomial that we don't know how to factor because it has 5 terms. We don't know how to factor that. But I'm telling you to solve it. So how in the world could you do that? Well, you can go to the old standby method of guess and check. I could pick a number for x and plug it in and see if it works. But how many options do I have for x? I have an infinite number of them. And I could be going at this literally forever and never actually find the answers. I don't want to do that. So this next theorem is incredibly powerful. It narrows that infinite number of possibilities down to a finite number. It's called the rational roots theorem. And it says that if I'm going to have a rational root, a simplified rational root, h over k, rational of course means it can be written as a fraction, so if I have a rational root, it can be written as a fraction. So if I have one of a polynomial equation with integral coefficients, then it must be the case that the numerator, h, is a factor of the constant term. So that's the term that does not have an x in it at all. And k, the denominator of my root, must be a factor of the leading coefficient. That's the coefficient of the highest power term, the term that gives me the degree of the polynomial. So for example, I've got this same polynomial that I wanted to solve a moment ago, and the rational roots theorem tells me that if I'm going to have a rational root, the numerator of that root must be a factor of the constant term, which is negative 9. The denominator of that root must be a factor of the leading coefficient, which is 2. So let's list out the factors of the constant term, negative 9. Well, 1 is always a factor, but so is negative 1. So I've got plus or minus 1. What are the other factors of 9? 3 and 9. So plus or minus 3 and plus or minus 9. I always have the option of going negative. What about the factors of the leading coefficient 2? Well, that's even easier. Plus or minus 2 and plus or minus 1. Plus or minus 1 and plus or minus 2. So what are the possible rational roots? Well, those are the fractions that I form by taking the factors of negative 9 divided by the factors of 2. So I would have, I could take 1 divided by 1, I could get plus or minus 1 if I divided those first two. I could take the factors of 3 and divide them by factors of 1 and get plus or minus 3. I could take the 9 and divide it by 1 and get plus or minus 9. I could take the 1 and divide it by 2 and get plus or minus 1/2. I could take the 3 and divide it by 2 and get plus or minus 3/2. And I can take the 9 and divide it by 2 and get plus or minus 9/2. So that means I've got 1, 2, 3, 4, 5, 6, 12 options for rational roots. If there's going to be a rational number that is a root, it has to be one of those 12 numbers. So I've taken an infinite number of possibilities and narrowed it down to 12. And all I would have to do then is try those until I find one that works. So I don't even necessarily have to try all 12. Now 1 is really easy to try. I can plug in 1 for x, And let me erase my circles here. Okay. So 1 to any power is always 1. That's why it's easy to try. So I have 2 plus 3, which is 5, minus 7, that's negative 2, plus 3 is 1, minus 9 is negative 8, and that's not 0. So 1 does not work. Negative 1 is also pretty easy to try, as long as I remember that negative 1 to an even power is positive, negative 1 to an odd power is negative. That would be 2 minus 3, that's negative 1, minus 7 is negative 8, minus 3 is negative 11, minus 9 is negative 20, and that's not 0. So I've ruled out 1 and negative 1. Now 3, I could plug it in like that and do the computations, or I could see what happens when I divide using synthetic division by 3. I know that if I end up with a remainder of 0, then 3 is a solution. Okay, so let's bring down the 2, multiply, add, multiply, add, multiply, add, 3 times 63, 189, add, I get 180, and 180, my remainder is not 0, so 3 does not work. What about negative 3? Okay, so we can try negative 3 using synthetic division. 2, 3, negative 7, 3, negative 9, bring down the 2, multiply, add, multiply, add, multiply, add, multiply, add. Hey, I got a remainder of 0. Awesome. That means negative 3 is a root. So I found one. How many are there? There's 4 of them. Well, let's make this easier. If negative 3 is a root, we can take our original equation and we could divide it by negative 3, but hey, I already did that, and I get 2x cubed minus 3x squared plus 2x minus 3. That was my answer when I divided by negative 3. So that means my original polynomial, when divided by x minus 3, or divided by x plus 3, I'm sorry, gives me 2x cubed minus 3x squared plus 2x minus 3. So now I just have to solve that. Okay? I know I still have the same possibilities for rational roots. 1 and negative 1 still won't work. 3 still won't work. It's possible negative 3 could be a double root, so I could check negative 3 again. And if I do, I'll find out negative 3 doesn't work. So for the sake of time in this video, I'm just going to kind of give it the answer. We could try 9. Not going to work. We could try negative 9, not going to work. We could try positive 1/2, not going to work. We could try negative 1/2, not going to work. Let's see what happens when we try positive 3 over 2. 2, negative 3, 2, negative 3. Those are the coefficients of my new equation, my cubic one that I know that I'm trying to solve now. Carry down the 2, multiply, add, multiply, add, multiply, add. Hey, I get a remainder of 0. Cool. That means that 3 over 2 is a root. So I've now found 2 of my roots out of the 4, but I've also broken it down now to a quadratic equation. So all I've got left is 2x squared plus 0x plus 2. If I can solve that, I'll find the other 2 roots. Well, that one's easy to solve. Because 2x squared plus 2 equals 0 means 2x squared equals negative 2. Divide both sides by 2. That means x squared equals negative 1. That means x equals plus or minus the square root of negative 1, which means x equals plus or minus I. So that means my other 2 roots are complex roots. So if I had tried the other possible rational roots, none of them would have worked. So my roots are the 2 rational ones I found, which remember were negative 3 and positive 3 over 2. And then the 2 imaginary ones that I just found, I and negative I. There are 4 of them. It was a quartic polynomial equation, a polynomial with degree of 4, so I knew there had to be 4. Here are your immediate practice problems. Number 1, how many roots does x cubed plus 125 equals 0 have? Number 2, find all of them. Number 3, list all the possible rational roots of 4x to the 4th plus 3x squared minus 1 equals 0. All you have to do is list them. You don't actually have to find which ones work. You just have to list out the possible ones. All right? That's the end of sections 8.6 and 8.7.